Hi, this is Shanti, and I'm going to explain the spectral temporal graph neural network for multivariate time series forecasting paper. The research at hand is to encapsulate the inter and the intra series in multivariate time series data. But the existing solutions are either good at capturing the temporal patterns or the intra series patterns, but they do not perform well together. And to tackle this problem, the authors of the paper propose to combine these ideas to implement a self attention mechanism to represent the graph structure, to combine GFT and DFT, to implement a spectral graph convolution layer, and to perform forecasting and backcasting. This is the overview of the architecture, where X is the multivariate time series input given to the model, and this is the latent correlation layer where the time series input is translated into a graph input. It is sent to a stemGNN layer with two stemGNN blocks. And this block is used to predict the next next few timestamps given a few timestamps as the feed input, and to also predict the previous timestamps given the current timestamps. And this is then sent forward to an output layer with a GLU and a fully connected sublayer. Given the architecture, let's define the problem statement. The problem at hand is essentially given k timestamps. The task of the multivariate time series forecasting is to predict the node values in the graph of the next h timestamps. And this is done given the graph structure G and the model parameters theta. And since we are predicting the forecast and the backcast, the loss function can be a combination of both. And this is represented by the squared error loss of the actual value predicted and the ground truth to the forecast. Now, in the inference phase, we adopt a rolling strategy where given a timestamp t minus k to t minus 1, x cap t is predicted. And in the next step, using x cap t, given the input xt minus k plus 1 to x cap t, the next output xt plus 1 is predicted. This is how it is done for the next hedge timestamps. Now, GNN based approach requires a graph structure, and in order to serve more general cases such as for traffic forecasting, COVID prediction, energy consumption prediction, we have to leverage the self attention mechanism in the latent correlation layer so that the graph structure is data driven. To perform this, a query and key is used to compute the softmax function and then obtain the adjacency matrix. First, given the input x, it is fed into a gated recurrent unit layer to obtain the state of the last hidden layer r, and this is used in corresponding to the learnable parameters wq and wk to obtain the query and key values. And this is then used in the self-attention equation to obtain the adjacency weight matrix. And this adjacency weight matrix is used to define the graph along with the input x obtained. The stemGNN block is then processed. The first step in the stemGNN block is GFT, which is graph Fourier transform. Graphs can be represented using a Laplacian matrix defined by the identity matrix and a diagonal degree matrix given the weight matrix. Now, given the Laplacian matrix, an eigenvalue decomposition can be performed to obtain an eigenvector U matrix and an eigenvalue matrix lambda. Using this eigenvector matrix U, a graph Fourier transform can be performed to obtain the output x cap, which is the spectral representation of the input x. And by multiplying this output with the eigenvector, the value x can be obtained. So once the graph Fourier transform is performed, the next step is to go through a spectral sequence cell. In the spectral sequence cell, the DFT and IDFT operations are used to translate the time series data, that is the spectral input data, into its frequency domain. Once the time series data is translated into its frequency domain, it is easier to obtain the features from the time series data. This is done by using a one dimensional convolution layer and a gated linear unit. And that is represented by this equation here. So, after performing discrete Fourier transform, the output is obtained in its real part and its imaginary part. And the operation theta represents the kernel of the convolution layer with size 3 in the experiments of the research paper. And this product here represents the Hadamard product, which is used in the gated linear unit layer. And finally, the result can be combined for the real part and the imaginary part to obtain the output of the spectral sequence cell. And then inverse discrete Fourier transform can be performed to translate the domain from frequency domain to time series domain. Once it goes through the spectral sequence cell, it enters the graph convolution spectral layer, where the main idea is to implement a graph Fourier transform given a Laplacian matrix L, represented by the identity matrix and the diagonal matrix. A decomposition is performed to obtain the eigenvectors and eigenvalue matrices, and then graph Fourier transform is performed using a function that is dependent on the eigenvalues and the parameters theta that are learnt over time. This layer is complex in terms of time complexity, with a time complexity of O of n cube, because of the amount of time it takes to compute the eigenvalue decomposition. Once the eigenvalue decomposition is obtained, the inverse graph Fourier transform is performed. And after this inverse graph Fourier transform is performed, the output is fed to two different fully connected neural network layers with a gated linear unit to learn parameters theta f and theta p for predicting the output yi and to predict the backcast x cap. And this backcasting branch helps in regulating the functional space of the time series data. It can be used to reduce the residual error. Now, these residual connections here are used to stack multiple stemGNN blocks. And in this architecture, there are two stemGNN blocks stacked. The output of the first stemGNN block is subtracted from the initial multi-series input to obtain the residue, and then the second stemGNN block is processed, and the output of the forecasted value of the first and second and the first and second here is added to obtain the final y. And this is then sent into an output layer which contains a gated linear unit with fully connected layers to generate the predictions y cap and x cap. Can be further trained by using the loss function. To give a general overview, a multivariate time series input is transformed into a graph representation by using a self attention mechanism. It is then sent to a stem GNN layer, which contains two stem blocks. Each stem block performs a graph Fourier transform to translate the graph input into its spectral domain. And then discrete Fourier transform is performed to translate the time series representation into its frequency representation to then obtain the features from the frequency domain. It is then translated back to its spectral domain and sent to a graph convolution layer to obtain the features of the temporal patterns in the data. It is then sent to an inverse graph Fourier transform operation to translate it back to its um, graph representation. and then fed forward to a fully connected layer to forecast and backcast the outputs. And these blocks can be stacked by using a residue and providing an additive output of the blocks, which is then fed forward to a fully connected layer to obtain to obtain the resultant output from all the blocks. Now, to study the model's performance, an ablation study was performed by the researchers by removing the latent correlation layer, removing the spectral sequence layer, DFT, GFT, residuals, and backcasting layers. And it is observed that everything has a role to play. Without the presence of each of this, the mean average error, root mean square error, and the mean average percentage error is seen to be increased. Without seek to seek indicates the importance of temporal patterns for multivariate time series forecasting. Without DFT, the transformer will not be able to obtain the features of the time series data in the frequency domain. Without the residual and backcasting layer, it demonstrates that the how predicting the previous value of x enhances the time series representation. And without GFT, it can be obtained that the advantages of capturing the structural information of the graph is lost. And without the latent correlation layer, the advantage of having to represent the graph automatically in the architecture is lost. And observing the results, it can be seen that stemGNN overall has an average of 8.1% in mean average error and 13.3% on root mean square error improvement compared to the best baseline for each dataset. And to further validate the performance of the latent correlation layer, a case study is performed on traffic forecasting where there are six detectors chosen and the correlation matrix from the learned data is plotted, and each column represents a sensor. And it is observed that the sensors that are close by together have a higher intensity compared to the sensors that are farther away from each other. And this represents that the latent correlation layer can not just be used for graphical representation but as well but also for visualization. And to further validate the main idea of combining graph Fourier transform and discrete Fourier transform, another case study was performed using COVID data, where the top two eigenvectors that are obtained by the eigenvalue decomposition from the Laplacian matrix is chosen, and it is visualized for the world data as well as Asian countries data. After performing graph Fourier transform, it can be seen that the line in the time series data is much more smoother, and this increases the generalizing capability. And after performing the inverse discrete Fourier transform at the end of the spectral sequence cell, it can be observed that the data patterns in the frequency domain are recognized. And this ensures smoother forecasting. To conclude, the major contributions of this paper involve combining graph Fourier transform, discrete Fourier transform, and deep neural network concepts to represent both the inter-series and the intra-series correlations jointly in the spectral domain. And the ablation studies further prove their effectiveness. It has also contributed in automatically representing the graph structure by using self attention without adding human priors. And it has also met high benchmarks by comparing its data with multiple data sets of solar energy, electricity, ECG, and more. And it has outperformed the existing models by 8.1% on mean average error and 13.3% on root mean square error. Coming to my final thoughts, the model can be further improved by reducing the time complexity of the stemGNN as applying the eigenvalue decomposition in the graph Fourier transform and in the graph convolution layer. is complex and time consuming. It can be further improved by implementing in real world data sets and using it responsibly. Thank you.